Okay. So we're going to talk about stochastic resonance, which in which you have a nonlinear system that when you add the right amount of noise, you can detect signals that would be previously undetectable. All right. So let's just kind of say intuitively is that, you know, if we want to detect a sine wave, right, and that's a kilohertz, right, you might say to yourself, well, if you had this signal that there's a sine wave in there and you want to find it, just take the FFT, right, and hopefully you'd find that there was a 1 kilohertz sine wave there. And you might think, well, let me just put a bandpass filter around it, right? But sometimes the amplitude is too small for the noise that's there, all right? And there's something called signal to noise ratio. And I just kind of draw this line like it's 0, right? So let's put it on a dB scale, right? We'll call that 0 dB or okay, and then, you know, minus 20, minus 40. And so where's the floor, right? So I'll just put that at minus 40 dB and I'll have this come up, right? So here, the peak is 0 dB from a floor, right? This is just noise here in the frequency domain, and there's 40 dB of difference, right? So, you know, that would be 10 to the 20 divided by 20 divided by 10 to the minus 40 by 20, and that would be the signal to noise ratio. And sometimes, you know, that noise, it's higher than that, right? And if that noise keeps creeping up, the difference between the background and what you're measuring becomes really faint, okay? If we, let's see. I have one. There's research. So this simulation takes a little bit of time, I believe. It's not instantaneous, and I'll tell you what it is in a moment. So it's a bit, these simulations are long. Okay. So we have a few things. And so this V is actual noise that we're adding to the system. And then these signals that are going high to low, back and forth, there's two of them, right? I'll explain what those are in a moment. And then there's this V here, right? So these are going from, plus or minus 4, right? And our signal that we're trying to detect is always going plus or minus 1 millivolt, all right? So if I want to look at the FFT, right, of all of those, I'm going to delete. So if we put this to a linear scale, well, it does look like it's 0, right? It's not 0, but it looks like it. But this would be, kind of what you would see with one of these plots. And if this is an RMS, so I have to multiply it by 2 square root, oops. Square root of 2. And there's our amplitude. All right, so that's there. We put it back in decibels. So you can see that this is the noise floor of the signal. And you might say, where did that noise come from? Well, because it's a digital simulation, there's finite time steps and there's finite precision, right? Even with 64 bits, dual, double floating point numbers, there's still finite precision. In fact, LT Spice, and I'm just going to start the allows you to control this. So LT Spice is always trying to make things faster at the expense of accuracy. And so this num digit 15 is saying, it's almost like in C when you call something a double, right? A double floating point number. That's what they're trying to say. So that'll just take some time to simulate. So we're trying to detect a faint signal and noise. Now this, I'm just giving you an idea that the noise exists, okay? In this case, it's just digital noise. But what's going on here is this is a Schmidt trigger. Notice how the feedback is coming in on the positive side. And what that does is cause so notice how this is positive, all right? So V out equals V in, oops, H of S, but it also equals itself times beta H of S, right? Because it's positive. And now when I bring this over onto the left-hand side, I'm getting 1 minus H of S. And if we just take the simplest model for frequency response of an op amp here and plug that in, we get AVS, right? 1 minus AV over S equals well, if you take the inverse Laplace transform of that, right, it's going to be proportional to plus T, okay, exponential increase. Now it's a little, this is a little more complicated, okay, and I have a derivation of it. There's actually 2 competing exponential decays, and it depends on where you start as to which one, there'll be which one wins. So there'll be an exponential decay up, and there'll be an increase up and one down. And it just depends where you start. If you start here, it'll go up. If you start here, it'll go down. All right. And so that's our nonlinear system, is this Schmidt trigger. Okay. So, which is normally used to filter noise, right? But we're actually going to add some noise and add a signal, right? That ultimately we want to detect. All right. And let's go back. Just something I wanted to show you. So I used more digits in my calculation. Okay. Here I let LT Spice do it, and the noise floor, let's call it minus 140 dB, right? But here I use 15 digits of precision, and notice the noise floor went down to below, you know, what's that, minus 230 dB, right? So it's a cleaner simulation. But in circuits, you can have noise introduced from a variety of sources. All right. So what's going on? This is the Schmidt trigger, and we're going to do 2 things. We're going to run it without this sine wave, and then we're going to run it with the sine wave. And hopefully, and now I'm just going to. So this is the output of the Schmidt trigger without the sine wave. And so you can just see this noise relatively flat and then starts to roll off here, right? Here's our input signal. Okay. And so let's now add okay. And now here's our output signal. And what we're going to be what we would measure is the ratio of this to this, okay? The fact that you might say, but wait, the noise is so low before we put it through the Schmidt trigger, why are we even bothering to do this? And like, well, this is just a pure simulation environment. This would be a more real environment where noise already exists, all right? But this FFT, actually you do a power, what's difficult is that everything's bouncing around. And so we do a power spectral density, which kind of averages everything out, okay? But so actually this reads in that data and automatically plots it. Now, this plot isn't particularly useful, except it does tell you that it was switching off and on. If the input noise is too low, the output of the Schmidt trigger won't go high and low. It'll just stay one spot or another, right? But you can tell, right? And so this curve here is taking this noise and just doing a curve fit. It's a Lorentzian fit as opposed to Gaussian, right? And then it takes what's the value of the curve, the estimated curve, and divides that into whatever the peak is, and you get your signal to noise ratio, in this case 16. And if I were to change the input noise level, right, I would, you're kind of changing the frequency that it'll best detect. So you can almost tune it by changing the input noise level, all right? Now, that's like maybe a little too, that's like what one would do, okay? Now, things to study, does the brand of, or the style of op amp affect it, right? What about the gain bandwidth? How about the open loop gain? What about the slew rate and all these other things? Even if I'm buying the same op amp, does it make a difference from run to run? And then there's something called the hysteresis, okay? So just a quick review of what this looks like if I ran this in time. Okay, so that's the input and that's the output. And you see it's going high and low, and there's like a trip point. At some point, it goes low. Then another point, it goes high. You don't really see it as well until you plot input versus output, okay? And so if you're low, you can keep bouncing around, the input can bounce around, but then it goes past a certain point and then it trips high. But now in order to go back low again, you got to go this way, okay? And so the noise, so now if I have noise superimposed in time, and I'm just bouncing my cursor around, the noise has to, if the noise is too small, it won't switch one way or the other. And if the noise is too big, it's just switching all the time. So the noise, the sweet spot is near these peaks. Same thing with the sine wave, right? This sine wave, if it's too big, it actually is just turning this thing off and on without stochastic resonance, okay? So the amplitude of the sine wave itself has to be below this hysteresis width, right? But yeah, the larger it is, the easier it is to detect. And so the Schmidt trigger is in fact the easiest system you can build to study stochastic resonance, but it is this phenomenon of changing, of adding noise to a system to better detect a signal, or a signal somehow gets enhanced. It's in every aspect of engineering. We just got done with a summer bridge program, and I had people find alternative examples. And there's a fish that, in order to locate its prey items, is using stochastic resonance to detect these faint signals of their prey items swimming around. All right. Even in our own brains, there's stochastic resonance. And ice age cycles can be need stochastic resonance to be able to explain it. All right. Now I put a link to this bit. All right. And this was a summer thing where I kind of had to review or assume people hadn't had courses yet. But if you get to scroll, now, yeah, RMS is an important thing because that's how we measure the noise. But noise actually needs two things. I'll just point it out now. So noise, the input noise will be an input, right? And what are we going to change? Noise does have frequency to it, right? And a perfectly uniform noise would contain all the frequencies. And there is a kind of way to use a noise source to generate a Bodhi plot. But the first thing we'll do is I just control, right? RMS, right? What is the RMS of that noise? So that would be an input. But there's the frequency component of this as well. And that's what I found is a little bit harder to find information on. So you kind of see that there's noise at all these low frequencies, right? But really, the simulation only runs for a second. So you'd only get one complete cycle of 1 hertz, right? So in order to get 1 hertz more accurately measured, I'd have to run the simulation for like 10 seconds, right? It should be just 2, but tends to be a little bit longer. And then you see the noise comes out, it's kind of constant-ish till about 20K, and then you see this roll off. And so in these experiments, what I found is they'll tell you the RMS, but they're not, I don't know, it doesn't seem they have a nice way of saying, this is the noise source that we're using, and what's the frequency component, okay? This is the noise source, and if I want the frequency component to be lower, I lower this number. If I want it to be higher, I raise the scale factor. But it seems in trying to repeat other people's work, they're a little bit quiet about really the noise source they're using. Now, some of this is just me trying to find out the minimum simulation parameters. So they can speed things up, but still get everything to work. That's not really so much, but anyway, this is. So what's going on? Probably should have started here, but I got excited. So the x-axis is position. Where is the particle, right? And the red line represents a double potential well, all right, in energy, all right? I can give you the equation in a moment. But the you can see the particle is here or it's there, right? And as the simulation proceeds, this bouncing around is because I've added a noise source, all right? And this going up and down is actually the signal you're trying to detect, okay? And if you add the right amount of noise, you can get that particle to hop back and forth in time with the beating of this, this warping of this function here, okay? But in our case, we're not going with position. It's either you're high or you're low, right? And we're adding the noise so that you can switch from high to low and get it out of one of these wells. Because if this wasn't bouncing around, it would never get out of the well, all right? Even if it's here, it doesn't completely flatten out. It doesn't get out of the well, it just stays there, okay? And so, there's some other cool videos here. But this is actually that potential well, something minus squared plus something to the fourth, right? And here's where the sine wave is coming in. So this here, right, dx, right, is that I take a snapshot in time. Oops. Taking a snapshot in time, that's that curve, okay? Oops. So that's that equation, okay? And now we have a differential equation, which is, we have the velocity, right, minus the derivative with respect to x, not t, right, plus, which turns, here's our sine wave that we're trying to detect, right? And then that's our noise source, okay? And so this is what we would want to simulate, but rather than simulate it in a differential circuit, we just integrate both sides. And so that's our position. Because in op-amp circuits, it's better to use integrators rather than differentiators because they have less noise. And so this is just a behavioral circuit, right? This is X equals the integration, and you need this scale factor, otherwise it won't work, right? Then you have XP is X prime, so that's the derivative, right? And it loops back in. There's our noise source. Here's our input. And if I run that, okay, that's my noise. And this, you kind of need, here's where it flattens out, and you need the RMS value, right? And then, there's some Python code to simulate that, all right? But so when I increase the noise amplitude, if you will, the theta is RMS. When I increase theta RMS, the full width half maximum of this is pushed out. And full width half maximum is, what's the width, right, when you're at half maximum? And so when I increase theta, this gets pushed out and out. When I decrease it, it comes in, all right? And so by just simulating this, right, I change the noise from 339 millivolts. Now again, this frequency response is always the same. So I change, I simulate it for input noise magnitudes, and then calculate the signal to noise ratio and the full width half maximum. and you get this plot. And that there, for a particular frequency, right, there'll be a peak that the noise level will kind of tune it in at. And this is not SNR, it's full width half maximum. And by doing a linear extraction here, you can actually back calculate some values. And there's the actually derive it full out using more 110 type stuff. Anyway, that's I know that's a lot, but things to study, right? So the Schmidt trigger is the easiest way to study, but you know, we have the op amp OP37, LT 1630, but I also have this field programmable analog array, which I'm just going to show you. So this you can download for free. And I have one set up in my office that you can access for free. So I'm going to zoom in and then see the chat. Yeah, sorry, Al, once I get talking. Anyway, this is a multiplier and you just put it down, right? And you wire it up. This is a summer with a built-in low pass filter, and you just tell it, I want, what's the corner frequency in kilohertz? What's the gain of the input 1, gain of input 2? And then you just have to set the clock, right? This whole business is a resettable integrator. Okay, see that little symbol? So you just have 2 inputs and then you control when it resets, right? So, you know, if I want to change the integration constant, I just type it in. And now this, my home computer isn't set up for it, but I just click this button and it programs the chip in about less time than it takes me to tell you about it. And then you, so there's no breadboards and pushing wires around. It's really a rapid way. So we could study this phenomenon with that, right? There's also other nonlinear phenomenon to study, like the quadratic integrating fire neuron, and then some other chaotic systems. But that's, it might be a bit much, but I do believe, where did I put it? So this slide is, that's that Google Doc. That's the Google Doc. And here's a whole manual on how to get it done. In Scopy. But yeah, if you had one of these ADLM kits, you could work on it, you know, not in your spare time. You could remotely log into this other computer and do it there as well. But yeah, I mean, it's a long manual, but you would have seen it all everywhere. You know, here's how to measure the Schmidt trigger. Here's You know, taking plots. All the Python code is provided, things like that. Anyway, that's just kind of an overview. You know, with these classes, I'm not exactly preparing the lecture ahead of time, so it's a bit off the top of my head. So sorry for the confusion.
So
Oh, hold on. Can you repeat that?
yeah,
Yeah.
question. So like, it sounds like the gist of this is, I'm hearing like something where you're actually adding noise, and it sounds like you're better able to recognize the signal by manipulating that to things
Yeah.
that you expect. Is there any chance you can like give a couple of examples of how this would be applied kind of more high level, you know, so I can kind of connect or like visualize it? Or I mean, probably in a lot of places, I'm just hearing it, and right, noise is a big thing. It's in a lot of stuff.
No, it's totally counterintuitive. I mean, the high level bit, right, is you have a system, right, and you have noise, and then you have some signal, and let's just call it, it's faint. Okay. Hold on, I gotta shut the door. So here's the thing. If I just had noise into the system, right, I would get out noise. If I just had the signal, I'd probably get noise. But when I add them both, right, it works. Now, yeah, this goes directly against superposition, where you could, you know, you look at the noise and then add the output to whatever that signal is. No, both have to be there. Now, now we're kind of going to get out of my area of expertise, right? But let's say this is time, right? And I have this, okay? And whatever this is, if I'm past this threshold, we're in an ice age, okay? So maybe it'd be better if let me draw it the other way.
We can't see your screen, by the way.
Oh, I forgot to share, sorry. Right, is that what you were saying?
Yeah.
Yeah, all right. Let me find my Zoom. Sorry about that. Yep. So it's Vishnu. Yeah, you're right. There's fault detection in machinery, and you know what I can do? Summary. I'm just putting a link to something. Now, the paper is really about running a summer program, but stochastic resonance is the thing we're doing. And where did I put it? Stochastic resonance was chosen for the summer bridge because stochastic resonance is a research topic in all engineering. Oh, I gotta fix that. It's gotta be. Actually, the paper got rejected. But so where did it go? I think stochastic resonance. So it's actually 20. There's something to do with bridges, failure extractions, mechanical fault diagnosis, photodetectors, and then there's a framework. So I think anyway, I'll have to go back and change that. But yeah, so then that paper, there's papers at the end, but I also think in the lab manual, there's a link to the actual, or I'm sorry, here. If you scroll down to the bottom, okay. There's the definition, that's like Wikipedia. That's the video. And then here's the original paper, right? That has all these applications, okay? And you can see here, applications, all right? But it's like grown a lot even since this paper was written. And yeah, this is the picture, okay? Is that, so anyway, so let's just call this temperature, right? And so whenever the temperature drops, there's an ice age, right? But of course, you know, let's call the yellow the real temperature, right? And it's kind of bouncing around. Now you still might be able to detect it. Well, actually you can detect an ice age because it's really, really cold, right? But you have this noise, right? So what's the inputs to the earth, right? You have sunlight, but that changes with what? Like sunspots, right? Well, that's the input, right? You know, you have CO2 levels, O2 levels. And the thing is like oxygen, I mean, it's just really interesting that in one ice age, it was the fact that plankton made a lot of oxygen that all of a sudden the planet went into an ice age. And since the planet was covered in white ice, it was reflecting all the energy back into space. And so it stayed that way for a very long time. All right. So you have all these inputs, but then there's this periodic signal. And I'm sorry, I do not remember it off the top of my head, but there's this periodic input. Could be sunlight, or it's actually, you know, the Earth's orbit around the sun, right? It doesn't follow the exact path each year. So there's this kind of faint signal that's periodic that based on the noise will kind of, so this ice age is happening periodically is an enhancement of that signal. All right. Now, again, that's just right off the top of my head. I haven't prepared and I am not claiming expertise on that. But usually when they talk about stochastic resonance, one of the first things they mention is ice ages. Okay. Now, other thing, something I just thought of is that, yeah, that's, what are, but in EE, you have analog to digital converters, and you can actually make them better by adding noise. All right. Of course, the right kind of noise, right? But that differential equation, okay, you can, yeah, you saw me do it in LT Spice, but you can also convert that to fixed point numbers, right, rather than floating point. And you can simulate that differential equation in a microcontroller, right? Like from TI or whatever, right? You can simulate it in an FP field programmable gate array that's digital, right? That was, you were using that in 118. The thing I just briefly showed you was a field programmable analog array where it's really linked right back to the op amps that we had done. And so the Schmidt trigger doesn't follow this equation exactly. It's like minus AX plus BX cubed, right? When I take the derivative, that's what I'm getting, right? So it doesn't follow that exactly. But you can implement this equation and make a numerical integrator and have it run on a microcontroller, right? Or a field programmable gate array. Or like I said, you could do it that way. You can even make an IC. If you look at, maybe even the, oh, sorry, I just saw the chat. Yeah. Anyway, here's the thing. And maybe, you guys are doing some good, you're researching on your own right now. The thing about the Schmidt trigger, like I said, is it's a really easy system. Although maybe even now microcontrollers are so cheap that even though they might be the easier system, and you could actually model that quartic relationship better. All right. But yeah, and actually now I'm thinking, Alex, your idea, oh God, what was it? It was Bluetooth and EKGs or something. Was that right?
Yeah, like
Okay.
a bracelet and all that. It's
Sorry.
gonna have a lot of noise, right? Movement.
Yeah. And so, so the thing is the noise might already be there, and then, which makes it hard to detect. But here's the thing, can we reduce the power by using stochastic resonance to capture the signal, right? So, and like so here's the thing, yeah, why I just picked the Schmidt trigger and I kind of go down the rabbit hole just because it's like, oh my God, it's an op amp circuit. It's got positive feedback. I could teach this to any, to transfer students fairly quickly and have them do a real project without, 10 courses in EE.
Are you saying that you could reduce the power? I'm hearing that you'd add noise. I guess I don't understand how that would reduce the power required for a system. Maybe that's beyond this.
No. All right. Do I know how to do that off the top of my head? No.
Oh no, that's okay.
But
Um,
but if you can, usually by adding more power, one way or the other, right? You can get a better signal, right? Let's even just talk about the radio, right? If you can't, if I'm trying to transmit to you and my signal is too faint, well, I increase the power of the transmitter, right? So, Bluetooth is pretty low power as it is, but can it be? So if I can detect a fainter signal, right, then maybe you can send a weaker signal, and that's where you would reduce the power on the transmit.
gotcha. So on the other end, like you have
Yeah. Now, a lot of
transmit and
times,
receiver.
I think what doesn't come out is that it can take longer to actually detect the signal. And like, what I haven't looked at, and just this straight example, right, is let's say I'm sending a signal. Well, can stochastic resonance detect an amplitude modulated signal? Can it do a frequency FM modulated? Probably, because if the frequency doesn't change that much, right? For FM modulation, because yeah, just detecting whether a sine wave is there or not. I mean, there's pulse. I mean, if the sine wave is there or not, you're actually sending a digital signal, right? So if I send 10 periods, that could be a 1, and send nothing, right? That can be a 0, right? And so just trying to figure that out, but actually reducing the power of transmission. That's just off the top of my head.
The documents you were showing us earlier, I was trying to figure out where they were. It looks like you had a Google Doc that was a jumping off point.
Well, you know what? I almost said, I'll put those in the comments.
On the left, that document.
Starting to lose, what I'm saying is this document, I thought I sent out to everybody. What's going on? Sorry. Chat. So that's that Google Doc, which was really, I felt that I needed to review certain things with the transfer students, then kind of go into stochastic resonance with maybe more. Actually, it was me trying to understand it better. Take care, Justin.
Okay, I'll just check my email. I didn't see it recently, but if you sent it a couple weeks ago.
I can send it. You know what? I'll send it out when I send out the fact that this meeting's recording is done.
Okay. And then a question I had is if like the LT Spice file is in one of those papers that you were looking at, or
It's
document.
in the manual.
Okay.
I mean, I have a whole zip drive where the LT, you just run the LT Spice file, and then you run the Python code, and it reads everything in. The only thing you have to do is change the paths. It's pretty I mean, I only ran into trouble with people who they didn't know resistor colors yet. I didn't realize some people hadn't learned that yet, right? They hadn't had that class, so I didn't really cover it. But if you, this is pretty self-paced. Now, yeah, sorry for just scrolling through so much. But now this is just, you've done this in 110 lab, right? And the Python one that comes after it, again, it's the same thing. I mean, I just cut and paste, right? And then I'm even doing circuit review. Oh, this thing is long. Oh God, it's long. So then it's, hey, this is what a voltage source is. This is, I mean, stuff that I guess too, I was practicing making things better in '98, right? But, thinking, it's simple, but sometimes going back and doing the simple can help you with the complex. Sorry. But most likely, eventually, right? Now we're getting into the Schmidt trigger. And actually, I found a better way. You just put these pins in. Oh my God, it's so much easier, right? And then you build a Schmidt trigger and you run it, you measure it, and then see, like, that red is always V plus, that blue with no stripe is always channel 2. That's always input 1. And the Schmidt, you can clearly, and yeah, telling people, hey, make sure about that notch, right? This is all things that blew up in my face this summer. But you go through and you do the Schmidt trigger and you measure the history. So this is like maybe more, because I don't even know if you did it in 122, just a regular Schmidt trigger. And then you go into this, here's the experiment, right? This layout's a little different, but I even have, it's, and then I actually do the experiment, right? And then I even plot it. And sometimes because it's noisy, you get weird stuff. Okay, does that make sense?
Yeah, and then the other thing was you showed us where the paper with the applications were, and I
Yeah.
didn't screenshot it fast enough. So if you can just show me where the link
it's
is.
in the, if you go to Summer Bridge,
Okay.
well, actually, it's referenced in this paper, and it'll be probably 19.
Okay, and is there somewhere we can access that, or?
Oh, I mean, you have to VPN into university, but then you get it from the library. But
Okay.
I do, but it's in the lab manual, right? Way at the beginning. It's,
Well, it's okay. It's not too big. I mean,
okay, so here's,
there.
so here's Research Club, Stochastic Resonance, right? Which is this, which then has, you have to just scroll to the bottom, which then has pretty much everything right there. It just doesn't have the lab manual or that paper. Okay, that's the lab manual, which has everything. And then the paper is just maybe a little simpler to see.
Okay, thank you.
Okay. But yeah, that's probably all we need to do for today. Just, probably gave you way too much detail on one day, but all the information is there. And all you really have to do is just type in a thing of your imagination in the phrase stochastic resonance, and something will come up. Okay. And, a lot of EE senior projects tend towards biomedical, right? And yeah, if you had biomedical friends in that department, maybe, yeah, you could even work with that. Okay. Just food for thought. That's all.
Sounds good. Thank you, Professor.
All right, guys, I'm gonna scoot. Oh, hey, Ryan. Yeah, you too. Hey, Ryan, nice to see you. Hi, Gilbert.
Hello.
Have a good
Yeah.
weekend. Hey, Vishnu,
This-
great question.
The link is needing for like a password. You need access.
What for what?
The link you posted.
It shouldn't.
I cannot open it.
It's Dropbox. You should be able to just download it. Anyway, don't worry about that link. It's all in the Google Doc. When I send out an email, I'm gonna send everything out again, okay?
All right, thank you.
Okay.
Can you give me just a minute to copy the chat? Because when you end the meeting, it's not going to let me.
Okay.
I think the chat
Alright.
is saved in the recording. But
Okay.
Right, but
sure.
you might not have it.
yeah,
Yeah,
Would
just-
you, do you have a copy of chat? I thought it saved it for me.
I've seen it.
Okay, I'm
get
good
to
now.
everything, But yeah, might as well save it now, just in case.
Yeah, we can save it. We have to like click save, and I did. Thank you.
That's okay. I'm not trying to cover up the evidence or anything.
All right. Well, have a great weekend.
You too.
Thank you.
Thanks, Professor.
All right. Thanks for coming.
See you next week.
Yeah.
See ya. Bye.
Bye.